Hello, we have discussed the method of finding bridges in the previous video, and now we are going to see the application of that concept in this video. And the name of the problem is Bertown roads from codeforces, having the rating of 2100. So we will see the problem and we will apply the same concept of finding the bridges. If you not watched that finding the bridges concept video, then first watch that video, then you will be able to understand. So let's come to the problem. What the problem is: you are given n junction and m roads, means n vertices and m edges are there, and these are bidirectional, but the traffic has increased, so the government has decided to make it unidirectional. So is this possible to make the unidirectional road from the given input data or not? We have to identify, and if it is possible, then you have to tell the order in which the nodes are connected, from which node to which node. So the input will be the n and m. N is the number of vertices, m is the number of edges, and for m lines we will be given the corresponding edges, and the output is going to be 0 if it is not possible, and you have to print the output as the order in which the nodes are connected, if it is possible to make the roads unidirectional. So this is the test cases. Two test cases are there. We will discuss these two test cases and understand the problem. So the first test case is going to be the graph like this, and the output is going to be like this. Okay, so dfs1 will be called from the main function, and whenever we will traverse any edge, if it is not unvisited, then it will be from parent to child, and if it is already visited, means the backage is there, then the node edge direction is from the child to its ancestor. So this is the thing that we are going to do, child to its ancestor, not the ancestor from its child, because while track backing it suppose here one from 1 you go to 2, it was not visited earlier, then 2 3 from 3, and 3 has connected to 1, means it is a backage. So since 1 is the ancestor of 3, we will push it inside the queue. Whatever we will get the direction, we will push it inside the queue, and after that we will print this out, or anything whatever we want to do with that edges, because we have got the edges, now we can do anything. So we will push inside the queue only if it is from ancestor to child to ancestor, not from ancestor to child. We have to take care while pushing the back edges. Okay, come here. From 1 it has gone to 2. In time of node was 0. 2 has got the in time as 1. See the in time from 2 to 3, and 3 to 1 has the backage. So we have pushed it inside the queue. Since the in time of 3 is greater than the in time of 1, so we have pushed it inside the queue, and from 3 it comes to 5. Since it was not visited, we have pushed inside the queue this edge. From 5 to 6, 6 to 4, 4 to 5, 5 was already visited. This is a backage, so we have to check whether the in time of this child is greater than the in time of this ancestor. So in time of 4 was 5 and in time of 5 was 3, means in time of child is greater than the in time of ancestor, means we can push this edge in the queue. 4 to 2, we will check, it is also a backage because 2 is already visited. So in time of 4 is greater than in time of 2. In time of 4 is 5 and in time of 2 is 1, means the child has a greater in time than the ancestor. means we will push it inside the queue. Track back 5 already visited, 3. So we have got the all the corresponding direction of edges in our queue, and we can push this out. We can print this out in the queue. So see the code what we have done. This is the dfs function only, simple, and this code is similar what we have discussed while discussing the finding the bridges. If it is parent, then we will just continue. If it is the package, then we will minimize the load time of the node, current node. And what we have to do if it is a package, when we have to push this inside the queue, if the in time of the current node is greater than the in time of the ancestor, so we checked. If it is that this case is true, then we will push that out, node and x. We will push this out from node to x. Okay. If it is not neither package nor parent, then it is a forward edge. Then we will just push it out inside the queue using the queue.push, and we will call the dfs function to the child. This is what this condition is doing. We have to see here what this condition is doing. When our answer is going to be 0, when it will be the bridge. Whenever it will be the bridge, it means that it can't be, we will not be able to make unidirectional roads such that we can reach all the edges. Because if this is the case, suppose this is the graph is there, this graph is there, and from this graph this is connected like this. So, like this is the bridge here. So if this is the bridge, then we can't give this direction also, this direction also. We can't give both direction. So this will separate this part of graph from this part, one part of graph from the other part of graph. So whenever we will find bridge, means that we can't assign the road as unidirectional. Even if we assign as unidirectional, then from one node to other node we will not be able to reach. From one node to every node we will not be able to reach. This condition we have also to fulfill, that we have to reach from one node to every other node. So whenever we will be finding any bridge, we will just break from this loop, for loop, and we will initialize the flag equal to 1, and inside the main function we will check it out. If the flag is 1, then it means that we have founded one bridge, and we have to output 0. Okay. So if when it is going to be the bridge, this was the bridge condition. If low of x is greater than the in time of node, then we will just break it out, and this is the same as the finding the bridges concept. So this, the only new thing was that we are pushing this inside the queue if the in time of node is greater than the in time of x, and here also we are pushing it out, and we are breaking it out if we find any bridge. So this is the new thing only, and now we can print this out, print this. So this was about the dfs function and how we can print this out. Come to the main function here, come to the main function. We will just dfs of 1. If flag equal to 1, then we have to output 0. If the flag is not equal to 1, then what we have to do? While not q.empty, we have to let c is equal to q.front. We will pop it out one element. D is equal to, we are storing this 2 since an edge contains two vertices, so we are storing these two vertices in C and D using q dot front and then popping it out. We are output C space then D then new line. So in this way it will print out all the q, and when the q will be empty it will just come outside the loop. So this is the code for an explanation for this problem, the Bertown rows, and this is a 2100 rating problem and we are solving it simply. So hope you have understood. Thank you very much.